In this paper, we investigate the relative performance of different types of language models on low-resource South African languages. The first question we'll need to answer is, what is a language model? A language model assigns a probability to a sequence of words. The probability is usually decomposed using the chain rule so that the model predicts words one at a time from left to right. At each step of this process, the model is given a sequence of context words and must predict the word that follows. For those who are new to this concept, you have likely interacted with a language model every day through the form of the predictive text feature of your phone's keyboard. Language models are typically trained on large amounts of data. However, the issue that we run into when we try to train language models for South African languages is that there is actually not that much data available.
So just how little data is there really? Well, compared to the Common Core English dataset like that was used for GPT-3, there's really very little. Naturally, there's a lot more data available for South African languages than just the sort of 10 or 12 megabytes that we're giving as an example here, but it's not collected in one easily accessible place and isn't of a high quality. Even considering this, the data available is orders of magnitude less than that which would be available easily in a language like English. So our three main datasets that we used contain approximately 1.2 million words for Zulu and about 1.7 million words for Sepedi, and we split these into training, validation, and test sets using a standard 80-10-10 split. For those of you that aren't already familiar, African languages are largely agglutinative, which is to say that the words are often made up of individual subwords, for want of a better phrase. This leads to very large numbers of unique words that may only be used a few times in the data. Using BPE, we're effectively able to model these subwords and provide a trade-off between word and character level tokenization. In the graphic, the underscore character denotes that the token is not a new word and actually carries on from the previous token. Moving on to the models that we've tested, we looked at using n-grams and feed-forward networks and had the unexpected finding that whilst higher order n-grams were more accurate, the feed-forward models provided better accuracy with smaller n-grams. Both model types trained very quickly, but as we will see later, produced poor results compared to LSTM and transformer-based models. For the LSTM and QRNN experiments, as a baseline we tested a simple LSTM model with no regularization beyond the standard input dropout, and predictably it was quick to overfit on the data. We then explored the use of the AWD LSTM architecture as proposed by Merity et al., and we found that larger models improved performance whilst the vocab size had little effect provided it was kept in a reasonable range of 2 to 10,000 tokens. This is dissimilar to other models tested where the vocab size did have an effect. Following this, we also tested the QRNN models and found that they trained slightly faster whilst still achieving strictly lower loss metrics than either the basic or AWD LSTM variants.
For our transformer model, we used the Hugging Face implementation of the GPT-2 architecture. The model hyperparameters were carefully optimized, and in the end, the best performing isiZulu and Sepedi models had similar total parameter counts. For regularization, we tuned the weight decay parameter of the Adam W optimizer and the dropout probability applied to all weights of the model. The performance metric we use is bits per character. The lower the value, the better the performance of the model. The results showed that the AWD LSTM and the QRNN performed similarly and outperformed the other model architectures. We hypothesized that this is due to the more sophisticated regularization methods that these models use. Interestingly, for these two models, the optimal hyperparameters were similar to those supplied by the original authors who trained the models in English. After the AWD LSTM and QRNN, the transformer was the next best performing model. Finally, the n-gram, feed-forward neural network, and basic LSTM models were the poorest performing models, though the basic LSTM model does serve as a useful baseline, showing that the advanced regularization techniques used by the AWD LSTM and QRNN models were effective. To investigate potential means of improving performance, we tried training models on combinations of languages rather than just one by concatenating the training sets. The results showed that increasing the number of languages generally improved performance on the target language. This highlights multilingual modeling as a promising direction for future work on modeling South African languages.